Control Systems Laboratory. In this video, we will discuss the digital simulation of a state space analysis. Coming to the title, Digital Simulation of a State Space Analysis. Coming to the aim, obtain the state model of the system by MATLAB simulation whose open loop transfer function is given by. So here open loop transfer function is there, S domain transfer function. From this S domain transfer function, this one we need to convert into the state model. That means in terms of matrix form, that only we call it as a state space analysis. S domain transfer function is the transfer function we need to find in terms of a state space representation. That is the matrix representation. X dot equal to ax plus bu and y is equal to cx plus du. The two equations only we call it as a state space model. State equation and the output equation. That is the first case. And next, coming to the obtain the transfer function of a system by MATLAB simulation whose state model is given below. So here already state model is, that means we know the ABCD matrices. We know the ABCD matrices, x dot equal to ax plus bu and y equal to cx plus du. That state equation or output equation is there. From this, again, we need to find the transfer function. That means reverse of previous one. Here already transfer function is there. From this, we are finding the state space. And in the next case, state space is there. From this state space, again, we need to find the transfer function. And also test the controllability and observability of a system. And also we need to check the controllability and observability of a system. Right. And coming to the experiment, first we need to cross check the theoretical calculations, how we are finding. That means here a transfer function is there. If you convert this one into the state space, how it will come, we need to cross check. In the same way, here already state space is there. This one, if you convert into the transfer function, what it will come. And also we need to cross check whether the system is controllable or observable. Once if you complete the theoretical calculations, then we will see the coding part, how we are developing the coding part, and we will see the simulation. First, coming to the theoretical calculations, first we will see the first case. That is transfer function is there. This one we will convert into the state model. So here we need to find the state model from the transfer function. State model from the transfer function. So this is the transfer function. Y of s by u of s equal to 10s plus 40 by s cube plus 4s square plus 3s. This is the transfer function is there. We need to split, we need to rearrange the transfer function properly. So that means y of s by x of s into x of s by u of s. So if we cancel the x of s and x of s, we are getting again the same equation. So we are splitting this equation properly. And 10s plus 40 by 1 into 1 by s cube plus 4s square plus 3s. So we are splitting the equation, transfer function properly. And before that, we need to cross check the how many state variables we need. In case of electrical circuit, if we take number of state variables depends upon the number of energy storing elements. So if you observe the circuit, what about the number of capacitors, what about the number of inductors and how they are connecting, based on that we can select the state variables. But coming to here, only transfer function is there. We don't know what type of circuit it is, whether it is electrical system or mechanical system or a combination, any other we don't know. So directly it's not possible. So by observing this highest power, by observing the highest power in the equation, here we are having s cube is there. So we are taking 3 state variables. Depending on the highest power, we are selecting the state variable. So here it is an s cube is the highest power. So we are taking 3 state variables. That the 3 state variables are x1 of t, x2 of t, and x3 of t. These 3 are the 3 state variables. Now we need to represent the total system in terms of state variable form, and then differentiation of the state variable form, that is x1 dot, x2 dot, x3 dot, we need to identify properly. So for that purpose only, we are splitting the transfer function into 2 transfer functions. That means y of s by x of s is one transfer function and x of s by u of s. Right? That means y of s by x of s you are taking as a 10 into s plus 40 by 1. This is the one case. And coming to the second case, x of s by u of s, which is equal to 1 by s cube plus 4s square plus 3s. Now if you observe, here totally in s domain is there. So cross multiply and rearrange the equation properly. If we cross multiply this one, y of s is equal to x of s into 10s plus 40. So if we rearrange, y of s equal to s into x of s into 10 plus 40s. So here also, if we cross multiply, u of s is equal to x of s into s cube plus 4s square plus 3s. Rearrange properly. So u of s equal to s cube into x of s plus 4s square x of s plus 3 into x of s. Now if we observe, it is a transfer function. It is in S domain form is there. But coming to the states model, state space, x dot is equal to ax plus bu. That means x dot of t is equal to a into x of t plus b into u of t. So there we need a time domain representation. So now we need to convert this S domain into time domain. Need to convert the S domain into time domain. So that means we are applying the inverse Laplace. So inverse Laplace of y of s is y of t, and here s into x of s is there. So that's one we can represent in terms of differentiation. In case of this state model, that state space analysis, that differentiation will represent with a dot. Differentiation we are representing with a dot. That means s into x of s means one time differentiation is there, so one dot. So x dot of t, and next 40 into x of s, 40 into x of t. So y of t is nothing but the output equation, right? And next coming to the u of s equation, inverse Laplace of u of s is u of t, and coming to the s cube. S cube means three times differentiation, so we are placing three dots. In state space representation, these differentiations we are representing in terms of dots. So here s cube means three times differentiation, so we are placing three dots, x triple dot of t, and 4 into s square x of s. So 4 is a constant, so s square, so two times differentiation, so x double dot of t. And next 3 into s into x of s, 3 is constant, so s into x of s, that means s power 1, one times differentiation, so one dot. Now in terms of dots is the equation. Now we need to cross check the whatever the state variables and whatever the differentiation of the state variables properly. So already we know the three state variables is the x1 of t, x2 of t, and x3 of t. So coming to the how we are assuming the state variables and the differentiation of the state variables means if the total equation will be in terms of x of t and its dots is there. So we are assuming x of t which is equal to x1 of t, x of t which is equal to x1 of t, and next differentiation of that x of t, differentiation of that x of t, that is x dot of t which is equal to x2 of t, x dot of t which is equal to x2 of t. So x2 of t is previously already x of t we have called it as an x1 of t. So x dot means again this one you can represent in terms of x1. If we represent means x1 dot of t, x1 dot of t, and next x dot of t is x2. Next x double dot of t we are taking as a x3 of t, x double dot we are taking as a x3 of t which is equal to also is equal to x2 dot of t. And next in our equation if we observe we are having three dots also is there, so x triple dot, x triple dot is equal, previously if we observe x double dot is x3, so default next x triple dot means we need to take as a x4 of t, need to take as a x4 of t. But why you are not taking x4 of t means in our case here we are having only three state variables. Three state variables means x1 of t, x2 of t, x3 of t only. We are not having a fourth state variable, so it's not possible to take the x4 of t. It's not possible to take the x4 of t. That's why this triple dot also we are representing in terms of x3 dot of t. That means in terms of x3 of t form. In our case, we are having only three state variables. That's why we are not showing anything in terms of x4. Now, once if identified these dots and all, then we can replace that equations with state variables. So coming to the first output equation, y of t. Y of t is equal to 10 into x dot of t. What is x dot of t? X dot of t is nothing but x2 of t. So 10 into x2 of t plus 40 into x of t. X of t is nothing but x1 of t. So x1 of t. So this is the output equation. And next coming to the other equation. Here u of t equation is there. If you observe this u of t equation, x triple dot of t. X triple dot is nothing but x3 dot of t. X triple dot is nothing but x3 dot of t plus 4 into x double dot of t. Double dot means x3 of t. So 4x3 of t. And next 3 into x dot of t. X dot of t is nothing but x2. So 3 into x2 of t. So this is the equation. And one more thing. Now we need to find the state model. State model means what about the equation? X dot is equal to ax plus bu. Ax plus bu. That means x dot of t is equal to a into x of t plus b into u of t. So we need to identify the x dot of t terms. That means differentiation of state vectors, differentiation of state variables. So x1 dot, x2 dot, x3 dot we need to identify. If we observe this equation, here already x3 dot is there. So if we rearrange this equation and identify the x3 dot, then we are getting x3 dot is equal to minus, that means these two terms we are shifting opposite side. So minus 4 x3 of t minus 3 x2 of t plus u of t is the x3 dot. And before that, here we are rearranged these all state variables under differentiation of that state variables. If we observe these equations directly, x2 dot of t is nothing but x3 of t is there. X1 dot of t is nothing but x2 of t is there. That two also we are taking. So here if we observe, x3 dot of t is there, x2 dot of t is there, x1 dot of t is there. So by observing these three equations, we can find the A and B matrices. That means x dot is equal to ax plus bu. That matrices we can develop by using these three equations. And at the same time, this y of t equation. By using this equation, we can frame the output equation. That is the C and D matrices we can identify. We will see how to identify that terms. Yeah. By observing these three equations, and this is the output equation. By observing these three, we can find the state equation. That is x dot is equal to ax of x dot of t is equal to ax of t plus bu of t. This one only called as a state equation. And y of t is equal to c into x of t plus d into u of t. This one we call it as a output equation. So first we will see what about the state equation, how we are finding. So coming to the state equation, x dot of t is nothing but x3 dot of t, x2 dot of t, x1 dot of t, which is equal to a into x of t. This is an A matrix, A into x of t. X of t is nothing but the three state variables, x3 of t, x2 of t, x1 of t, plus B matrix, B into u of t, B into u of t. Now you observe, first you will take the x3 dot of t equation. So this is the x3 dot of t equation. In this equation, what is the x3 of t coefficient? X3 of t coefficient is minus 4. And next, what is the x2 of t coefficient? X2 of t coefficient is minus 3. And next, what about the x1 of t coefficient? Here we are not having the x1 of t term. Here we are not having the x1 of t term. So 0. And next, x2 dot of t equation. We are taking now x2 dot of t equation. So here x2 dot of t is equal to, we are having only x3 component is there. X2 component and x1 component is 0. So here we are having only x3 component, that two coefficient is 1. So x3 component is 1, coefficient is 1, and remaining x2 component is 0 and x1 component also 0. And next, x1 dot of t. And if we observe the x1 dot of t, here we are having only x2 component is there. The two coefficient is 1. Only x2 of t coefficient is there. Remaining x1 and x3 is 0. X2 of t coefficient only is there. X1 of t coefficient and x3 of t coefficient is 0. So x3 of t coefficient is 0. X1 of t coefficient is 0. X2 is there. So that one coefficient is 1. So this is the A matrix. This is the A matrix. And next, coming to the B matrix. How to identify the B matrix? B into U of t. So again, in these three equations, we need to cross check whether any U of t term is there or not. So first we will check in x3 of t term, x3 of t equation. So here x3 of t equation, any U of t term is there? Yeah, here it is the U of t term plus U of t. That means coefficient is plus 1. So x3 of t coefficient is, x3 dot of t coefficient is 1 into u of t, b into u of t. Yeah. And next, x2 dot of t, here we are not having any u of t term. In x1 dot of t also we are not having any u of t term. So 0, 0. Right? That is the B matrix. So that equation only call it as a state equation. x dot of t is equal to a into x of t plus b into u of t. So from this equation, we identified the a and b matrices. This one only called as a state equation. And now we need to identify the output equation. Output equation, that is from y of t. So already y of t is equal to 10 into x2 of t plus 40 into x1 of t is there. By observing this one, we can develop the second one, that is the output equation. So y of t is equal to c into x of t. X of t is nothing but the state variables, x3 of t, x2 of t, x1 of t. So first you need to check whether any x3 of t coefficient is there or not in this equation. No, we are not having the x3 of t coefficient. So 0. Next, x2 of t coefficient. Any x2 of t coefficient is there? Yes, it is there. Plus 10. So 10. Next, x1 of t coefficient. Any x1 of t coefficient is there? Yes, it is there. 40. So 40. This is the C matrix. Plus d into u of t. D into u of t. So now we need to cross check in y of t equation. Any u of t term is there or not? No, here we are not having any u of t term. So it is a 0. So D matrix is 0. So now we identified the A, B, C, D matrices. This equation only, these two equations only, we call it as a state model. This is the first case. They gave the transfer function. From the transfer function, we identified the state model. This is the first case. And now we will see the second case. Yeah, coming to the second case, here you need to find the transfer function from the state model. That means they are giving the ABCD matrices. Giving the ABCD matrices, and by using that matrices, we need to find the transfer function. So already we know the formula for transfer function directly. So y of s by u of s is nothing but the transfer function, which is equal to c into si minus a whole inverse into b plus d. So this is the equation. So already we know the ABCD matrices. Directly we can substitute, and if we simplify, we will get the final transfer function. So we know the already ABCD matrices. If we observe this equation, first we need to cross check the si minus a, and then we need to apply the inverse, and then c into this si minus a inverse we need to multiply, and that one into b plus d. That is the final transfer function. In that sequence, we need to simplify and find the transfer function. So coming to the first step, we need to identify the Si minus A, where I is the identity matrix. So S into A is a 3 by 3 matrix. So identity matrix also we need to take 3 by 3. So S into 1 0 0 0 1 0 0 0 1 minus A matrix. Now if we simplify this one, here S into 1 S minus into minus plus, so S plus 4. And next, here it is in 0, minus into minus 3 plus 3. And next 0, 0. And next 0, minus 1. So minus 1, S 0. So directly S. And next 0, 0, 0. And next element also here also 0, here also 0. And next here it is in 0, here it is in minus 1. And here S into 1 S, and here it is in 0, so S. So this is the Si minus A matrix. Once if you are finding the Si minus A, then you need to check them. We need to find the Si minus A whole inverse. Si minus A whole inverse. How to identify the Si minus A whole inverse? Means adjoint of Si minus A inverse transpose by det of Si minus A. How to find the Si minus A whole inverse? First we need to check the adjoint of this one, the transpose by det of Si minus A. First we will check the det of Si minus A, and then we will see the adjoint. So coming to the det of Si minus A. So det of Si minus A means S plus 4 into AD minus BC. That means S into S minus this one 0. So S plus 4 into S square minus 3 into, now minus 1 into S remaining is 0. So minus 3 into minus S. And next plus 0 into. So 0 into anything will be 0. So this is the equation. So if we simplify this equation, we are getting S cube plus 4S square plus 3S. This is the det value. This is the det value. Det of Si minus A. Det of Si minus A is S cube plus 4S square plus 3S. And next, now det value is there. Now we need to find the adjoint of Si minus A whole inverse. How to find the adjoint means first element if you want means first element if you want means we will remove the first row and the first column, cross multiply these two. If we cross multiply with these two, we are getting the s square minus 1 into minus into minus 1 into 0. So only s square we are getting. This is the first term. And next, now we need to check the second term. How we are finding the second term means we are finding the second term is now we need to find the second term. So we are removing the first row and the second column. Now you multiply AD minus BC, that means minus 1 into S 0, so minus S, so minus S. And then now we need third element. So third element means the same that row we are removing and the last column we are removing. Now minus 1 into minus 1 plus minus this element. So minus 1 into minus 1 will be the plus 1 will come, minus 0 into S, so 1, right? And now coming to the second row first element. If you want the first element, again we will remove that particular row and that particular column. That particular row and that particular column we will remove. Now we need to identify this second row first element. That means this row we are removing and this row, this column we are removing. Now 3 into S minus 1 into 0, so 3S. So 3S. We are taking minus means after finding all the elements. After finding all the elements like this, you need to find all the elements. Once if you are finding all the elements, we need to change the sign. So here we are multiplying with plus, minus, plus, and the next will be the minus, plus, minus, and again it will be the plus, minus, plus. Like this we need to multiply these signs. We need to change that signs, right? Once if we are changing the signs, then we are getting this the matrix. Adjoint of Si minus a whole inverse is the matrix, and for that again you need to find the transpose. How we are finding the transpose means here we are having a column, that one we are writing as a row. Here we are having a column S square minus 3S 0, that one here we are writing as a row. The same way next column we are writing as a next row, and next column we are writing as a next row. This is the adjoint of Si minus a whole inverse transpose, right? And then how we are finding the Si minus a whole inverse means adjoint by det value. Adjoint by det value. So already here adjoint is there and det value is there. So here each and every term we need to divide with a det value. So already det value is there. So S square by S cube plus 4S square plus 3S minus 3S by. So each and every term we are dividing with a det value. So whatever the equation it will come. So if we represent this equation will come like this. Si minus a whole inverse is equal to each and every term divided by the det value. So this is the equation. S square plus 3 S square by S square plus 4S plus 3 square minus 3S by S cube plus 4S square plus 3S, like this each and every term. And now what is the formula? C into Si minus A inverse B plus D. So now we identified this value. So now we are placing the C matrix and D matrix. We need to multiply. So this is the C matrix and this is the D matrix. So first we will multiply the C into Si minus the whole inverse. So it is a row matrix. So we are multiplying this row with this column. With this row and this column. So 0 into the first term, 0. 0 is into the first term, 0. And next 10 into this term. So plus 10 into second term. Next plus 40 into third term. 40 into third term. This is the first row and first column. And next row and second column. Row and second column. If you multiply 0 into the first element, 0. Next 10 into the second element. So this is the 10 into the second element. And then 40 into the third element. So 40 into the third element. So this is the row into second column. And next same row into last column, third column. So 0 into 0, 0. And 10 into 0, 0. And then 40 into the last term. So 40 into the last term. Now this is the matrix we are having. So this is the C into SM minus a whole inverse. So this matrix into B matrix we need to perform. D matrix is 0. So anyway, D matrix is 0. No need to add anything. So if we simplify this 3, that is the final transfer function. Okay, D matrix is 0. So now this the matrix is there. So now this the row is there. This row we need to multiply with this column. We will see. So yeah, this the row is there. This row we need to multiply with this column. With this column. So the first term into 1. The first term into 1 means 0 plus 10 into this term plus 40 into 1. So this is the term. And next this total term into 0. This total term into 0. 0, 0. Right? If you multiply this complete row with this column means only first term will be there. Remaining will be 0, 0. So if you observe the first term, denominator is same, s cube plus 4s square plus 3s. Here also denominator is same, and come into the numerator 10 into s plus 40. So this is the transfer function. If we observe clearly, first case we are taking a some transfer function that we are converting to the state model, and come into the second case, already state model is there, that one we are converting to the transfer function. If we observe both the cases, we are taking the same one. That means first case, what is our transfer function? The same thing, this one only. First case, what is the transfer function we are taking? This one only. This one we are converting into the state model. And that state model ABCD matrix is the same one we are taking for the second case. And if we are converting that one into the transfer function, we are getting the same. Right? So this is the second case. And now coming to the next, that is we need to check the controllability and observability. We'll see first controllability. How to check the controllability means by using the Kalman's test, we can identify the controllability. By using the Kalman's test, we can identify the controllability. In Kalman's test, how we are identifying means we need to frame the controllable matrix Q suffix C. We need to find the controllable matrix Q suffix C. Once if we are finding the controllable matrix, then we need to find the det value. If the det is equal to 0, it is not controllable. If det is not equal to 0, then it is a controllable system. So first we need to check the controllable matrix. How to find the controllable matrix means B, A, B, A square B, so on up to A power n minus 1 B. A power n minus 1 into B. What is n value? N is number of state variables. N depends upon the number of state variables. In our case, we are having 3 state variables. So n, if you substitute as a 3, then you are getting 3 minus 1, so 2. So that's why up to A square B we are finding. This one is the controllable matrix. QC is equal to B, A, B, A square B. Already B is there. Now we need to find the A into B and A square B. So first we will check the A into B. So already A matrix is there, B matrix is there. If you multiply these two, that means here a row and column. So minus 4 into 1 plus minus 3 into 0 plus 0 into 0. So we are getting minus 4. And next, this row and this column. This row and this column. If we are finding, we are getting minus 4, 1, 0. This is the A into B matrix. And now we need to find the A square B matrix. How to find the A square B matrix means this is the A matrix, A into B matrix. So first you need to multiply A into A, and that matrix will multiply with the B. Then we are getting this one, 13 minus 4, 1. A square B, A into B. First we will multiply A into A, and that matrix we are multiplying with B. So there we are getting the A square B. So this is the matrix. Now we know the B value, we know the AB value, A square B value. That values we will substitute, that only called as a controllable matrix. So B matrix 1, 0, 0, and AB matrix minus 4, 1, 0. And next A square B matrix. A square B matrix is 13 minus 4, 1. 13 minus 4, 1. So this is the controllable matrix. Now we need to find the det for this matrix. Now we need to find the det for this matrix. Whatever the det for this matrix will come 1 into AD minus BC. So 1 into 1 minus 0. So 1 Next minus 4 into second term 4 into this row and this one you are removing. So 0 into 1 0, it is 0. And next 13 into means this first row and this one. Here also 0 into 0 0. So 1 into 1. So we are getting det value as a 1. If the det value is 1 which is not equal to 0, then we are saying system is controllable. We need to find the controllable matrix. Once if we know the controllable matrix, then we need to cross check the det value. Based on the det, if it is not equal to 0, then we are saying as a controllable system. Next, coming to the observability. Here also we are using the Kalman's test. By using Kalman's test, we need to find the observable matrix. This is the observable matrix Q naught. Q naught is equal to C transpose A transpose into C transpose A transpose square into C transpose, so on up to A transpose over n minus 1 into C transpose. What is n? N is the number of state variables. Here we are having 3 state variables are there. So 3 minus 1, 2. So A transpose square into C transpose. Up to this value we need to identify. So how to find the transpose first? We already know the C matrix. Here it is in row. That one if we convert into the column, that only we call it as in C transpose. And now coming to the A. Here it is an A matrix. How to find the A transpose means here row we are converting as a column. Row we are converting as a column. Row we are converting as a column. So this is the A transpose. Once if we know the A transpose and C transpose, then we can frame the observable matrix Q naught. So C transpose is there. Now we need to find the A transpose into C transpose. So already we know the A transpose and C transpose. If you multiply this one, we are getting A transpose into C transpose in the same way. Next, A transpose square into C transpose means already we know the A transpose. So A transpose into A transpose into C transpose. So first we will multiply the A transpose into A transpose, and then that one we are multiplying with the C transpose. Then we are getting this term. So now if we substitute all three together, that is the observable matrix. So C transpose already it is there, 0, 10, 40 is the C transpose. And next A transpose into C transpose is 10, 40, 0. 10, 40, 0. This is the A transpose into C transpose. And next A transpose square into C transpose. This is the last column. So now again this is the observable matrix. Again now we need to find the det value. If you find the det value, it will not come as a 0. If you simplify this one, it won't be a 0. So it is an observable matrix. You can check this one. Check the det value. It won't be a 0. If the det value is not 0, then that one is an observable matrix. So these are the theoretical calculations. Once the theoretical calculations is over, then you need to check the coding part, how you are writing the coding, and then we will see the simulation. So first we will see the coding part. Coming to the first case, coming to the apparatus required, personal computer and MATLAB software, and coming to the programming part, is the transfer function is there. This transfer function we need to convert into the state space. We need to convert into the state space. So here transfer function is numerator and denominator. So we are representing the numerator and denominator coefficients. So first coming to the numerator, highest power is S41. So S41 coefficient is 10. And next S40 coefficient is 40. So this is the numerator. And coming to the denominator, highest power is S cube. So it is S cube coefficient 1. And next S square coefficient 4. And then S power 1 coefficient 3. S power 0 coefficient 0. So this is the numerator and denominator. Once if you know the numerator and denominator, we can frame the transfer function. And how we are converting that one into the state space means, in state space we are using the ABCD matrices. Square bracket ABCD is equal to TF to SS. That means transfer function to state space of numerator comma denominator. This is a predefined command. TF to state space. TF is transfer function converting to the state space. TF to SS. TF is transfer function. SS is a state space. TF to SS of numerator comma denominator. So directly it will give the all ABCD matrices. That is the state space representation. That is the first program, first case. And next, coming to the second case. In the second case, we know the state model, that means ABCD matrices is there, but we need to find the transfer function reverse. State model is there, we need to find the transfer function. So we know the here it is a matrix representation. How we are representing the matrix representation is if we observe A matrix, row, next row. How we are showing this difference means here if we observe -4, -3, 0, semicolon. That means next data it will take as a next row 1, 0, 0, semicolon, and next row. So 3 rows we are showing. The same way coming to the B, 1, next row, 0, next row, 0. So here we need to place a semicolon, 1, semicolon, 0, semicolon. Then only it will take as a 3 rows. And coming to the C, only one row is there, no need of a semicolon. Directly we can place. D matrix is 0, only one element. Directly we can write. So once we need to enter the ABCD matrices, then we are taking a variable SYS. Any variable you can take. SYS equal to state space of, SS means a state space of this ABCD matrices. State space of this ABCD matrices. Now by using this state space, this variable, we can find the transfer function directly. Y is equal to TF of this variable. TF of this variable, directly it will come the transfer function. Directly it will give the transfer function. This is the second program. And coming to the third one, that is controllability. Here also we know the state space representation, that means matrices and all. By using these matrices, we need to find the controllability and observability. If we observe this, both the programs almost the same. In controllability, we are finding the controllable matrix. Observability, we are finding the observable matrix. There we are finding the debt in theoretical calculations, but here we are finding the rank of the system. We are finding the rank of the system. Here also we need to enter the matrices. So 3 rows, that how we are showing is with semicolon. So first we are entering the -4, -3, 0, semicolon, next row 1, 0, 0, semicolon, next row. Coming to the B, only one element, next row, one element, next row. So 1 semicolon, 0 semicolon, 0. This is the B matrix. C is only single row, no need of semicolon. Next, D is only one element. If we observe in observability also the same, only A, B, C, D. And then this all in the state space. So some variable, any variable you can take. SYS is equal to state space of ABCD. State space of ABCD. Now for that state space, we need to find the controllable matrix. So this is the controllable matrix, CTRB of this system. For this one, we need to find the controllable matrix, that only are assuming as a CO, controllable matrix, CTRB of this system. And now we are taking one more variable, any variable you can take, no need to take UC only. So length of A matrix, length of A matrix. And then Y is equal to rank of this controllable matrix. We are identifying rank of this controllable matrix. Now whether this rank and length are same, then that one we called as a controllable system. We are checking the rank of the system. Previously in theoretical calculations, we are checking the debt, and coming to the programming part, here we are checking the rank. In the same way, if you observe the observability matrix, also the same only. Once we need to represent this all ABCD matrices, state space, and from that we are finding the observable matrix. This also any variable you can take. Observable matrix for this state space, and then we are checking the length of this A matrix and rank of this observable matrix. So this is the coding part. Once the coding part is okay, then we will see the simulation part. We'll see the simulation. So already programming part, everything is there in a slide. So directly I'm copying the program. So we'll copy first case, that means transfer function to the state space. Copied. Come into the MATLAB. We'll open the new script. So the first line will be the CLC. It will clear any previous data in command window, and we'll paste the program. Yeah. You can check the programming part. Numerator denominator transfer function, and state space directly transfer function to the state space. We'll save the file. Let it be the same name. Saved the file, and now we'll run the program. We'll run and check the data in command window. Already numerator and denominator. Check. Numerator is there, denominator is there. This is our transfer function. For this transfer function, we are finding the state space. For this transfer function, we are finding the state space. You can check A matrix, directly it came, B matrix, C matrix, D matrix. You can compare the values also. A, B, C, D matrices. This is the first program, transfer function to the state space. And next, coming to the second program. Coming to the second program, now state space is there. From that state space, we need to find the transfer function. So directly we'll copy the program from slide. So this is the second program. Copied. We'll open the new tab, and the first line will be the CLC. It will clear the command window. We'll paste the program. So the A matrix, B matrix, C matrix, D matrix, C state space of that one directly we are converting it to the transfer function. Save the file. Let it be same name. Save. Now we'll run the program. Yeah, you can check in the command window. You can check in the command window. So this is the A matrix data, B matrix data, C matrix with respect to the state variables. Everything is there, and directly from this transfer function. So if you observe 10s plus 40 by sq plus 4s square plus 3s, that is previously what we are taking the transfer function. For first case, the same thing it is coming. Right, so this is the second program, state space to transfer function. And next, coming to the next case, that is the controllability. We'll copy the program. We'll take one more tab. First line is CLC, and then paste the program. A matrix, B matrix, C matrix, D matrix, state space of controllable matrix we are finding, length of the A matrix, and rank. Now we'll save the file. Let it be saved. Now run the program. Now you can check the rank. A matrix, it is a 3 by 3 matrix, B matrix, C and D matrices. So this is the controllable matrix. Previously, we are finding by using A and B matrices, B, A, B, A square B. Separately, B, A, B, we are finding A square B, the same term. This is the controllable matrix. Theoretically, we are finding, and for that we are finding the edge, and directly we are saying whether it is a controllable or not. Here also, you can check. Length of the A matrix is 3, and this one rank of the matrix is 3. So it is a controllable matrix, controllable system. So it is a controllable system. Right, so this is the controllability. Next, coming to the observable T-test, we'll copy directly from the slide. C. Open a new tab. And the first line is the CLC. It will clear the previous data. Paste the program. ABCD matrices, state space, and then observable matrix, length of the A matrix, and rank of observable matrix. Save the file. Let it be the same. Now save, and now we'll run the program and check the command window. You can check the command window. So A matrices with respect to the state variables, B matrix with respect to the state variable and the input, C matrix and D matrix is there. And this is the observable matrix. Previously we are finding C transpose, A transpose into C transpose, A transpose square into C transpose. Separately we are finding under that group. This is the observable matrix. For this observable matrix, previously we find the det which is not equal to 0. So it is the observable matrix. The same thing here, we are checking the length of the matrix. A is 3 and rank of the matrix is 3. So it is a observable system. So this is the simulation part. This is the simulation part. And coming to the conclusion, so coming to the conclusion, so the given transfer function we convert into the state model, and also the vice versa. That means the first case they gave the transfer function, that one we are converting into the state model. And again in the second case, state model is there, that state model also we converted into the transfer function. Both state model to the transfer function and transfer function to the state model. And now for the same system, we are checking whether the system is controllable or not. The same system we are checking the observable or not. The given system is controllable and also the observable. Both theoretically we observe and also in simulation also we observe. That means in terms of theoretical means by observing the determinant, and coming to the simulation means by checking the rank of the system. That is the rank of the controllability, rank of the observability, which is same as the order of the system matrix. In theoretical calculations means we are finding the det value. Det is not equal to 0, then it is a controllable and also a observable. There is observable matrix and controllable matrix. In the same way, coming to the simulation, here we are checking the rank of the observable matrix, rank of the controllable matrix, which is same as the order of the system A. Length of the system, we are finding that 2 is equal, then it is a controllable or observable system. So coming to in our case, the system is controllable and also observable. Thank you.